Right. First of all, thank you for inviting me to talk. I'm quite excited about this. It's a really, really weird object that has no clear answer. So that's the punchline. I don't know what it is still. Okay. Uh, so I'm just going to go through. It's so GRB 250702b is maybe a GRB, maybe not. So I'm just going to talk a bit about GRBs and then all the discovery and the narrative of finding it, and then all the possible models. As you can see, there's quite a few. And then it has some wider implications that are a bit weird. I'm going to focus on a couple of them very briefly. Okay. Oh. Okay. This slide is probably, I don't really need to show it, but broadly speaking, we've got this picture of two kinds of GRB. Obviously, it's a bit more complicated now. We've got short, hard GRBs and long, soft GRBs, and they seem to come from different progenitors. Long, soft come from collapsars, and short, hards from mergers, and they're accompanied by supernovae and kilonovae, respectively, in theory. And then, of course, we've got things like 211211A, which is right in the middle of the long, soft, and then has a kilonova. So who really knows? Okay, there's another exception to this, which is relevant for GRB 250702b, and that's ultralongs. So these are much, much longer than typical long GRBs, which are maybe 1,000 seconds. You can get up to about 10 to the 4 seconds with them, and they've got much more complex light curves. So 050724 is just a random long GRB I chose. And you can see this sample of ultralongs is much, much longer and very weird. So we've got things like the giant X-ray bump in 121027A. And in fact, sometimes they can even re-trigger gamma ray instruments. So yeah. And then again, like 250702b, the origins of these GRBs are very unclear. They might be some kind of weird collapsar. They might be some kind of TDE. Okay, but the important thing is that pretty much all GRBs are singular events that don't repeat. So this is a repeating GRB. So you can see we've got 3 main triggers. And what's really interesting is that this is periodic, or appears to be. So there's about 1,400 seconds rest frame between these two, and then we skip a couple of beats, but this is about 4,200 seconds rest frame away. Okay. Yeah. Okay. So it was detected back in July. It's just over a year old now. And like I said, there are multiple outbursts, and they were observed by multiple instruments. So we've got Fermi, Conus Wind, Swift, Maxi, and Psyche, which I didn't realize was a mission to study an asteroid and just happens to have a gamma ray spectrometer on it. So that puts the engine duration at several 10 to the 4 seconds minimum. And we've also got this possible periodicity, as I said. In the GRBs itself, it's got a fairly short minimum variability timescale, certainly more typical for a collapsar or a long GRB than, for instance, a jetted TDE. And the spectrum reaches to mega electron volts, so pretty high energy. But altogether, this repeating behavior, this ridiculously long engine duration is completely unique, or pretty much completely unique in 50 years of GRB astronomy. So that might mean it's not a GRB. And in fact, the first assumption that I was aware of that it was galactic. But then EP found an X-ray precursor by looking back through the data, and that has actually been on for a full day before the GRBs themselves were detected, and that pushes the engine duration to 10 to the 5 seconds or so. But importantly, it's also allowed localization, which was, as I'll show in a couple of slides, very, very difficult from the ground. So yeah, you can see EPW, the WXT source there. So the problem is, now we had a bit of a location to look in. You could actually follow up with deep IR imaging. And here is the counterpart. You can see just how red it is compared to the stars around it. So it is on a Milky Way dust lane. But yeah, I'll show the galaxy in a sec. But most importantly, it's consistent with an with an extended source. So we know it's extragalactic. It's in another galaxy. So this is from Wei's paper. And it's a really, really nice image of the galaxy. You can see that the location of the source is nicely offset, and it's right in the middle of this dust lane. So you've not just got dust in the Milky Way, you've got a ton of dust in the way in the host galaxy, which basically means you have a little bit of IR and then just X-ray and radio to go on. So in terms of X-ray, it's broadly consistent with a t to the minus 8 to t to the minus 9 slope. So that's kind of quick. It's also not consistent with the canonical fallback timescales. So in a tidal disruption event, you have this either t to the minus 5/3 if you've got a complete disruption, or a t to the minus 9/4 if you've got a partial disruption. And that slope, the 1.8 to 1.9 kind of fits nicely in the middle of those. So not really consistent with either of those, which might rule out a TDE in some ways, but I'll show later that that doesn't really matter. And it's also not consistent with ultralongs. So it's far, far longer than ultralongs. You could kind of shift the ultralongs around a bit. It's difficult to know exactly when to put the trigger time. So this is the X-ray light curve of 250702b. And then the vertical gray lines are the different Fermi triggers. So yeah, you can shift the ultralongs around, but they're pretty much not very consistent. 121027A kind of is at later times, but it's very luminous in itself. But yeah, it's much slower, much longer timescale than ultralongs. So it looks like it's a very different progenitor to any kind of GRB we've seen before. Okay. In IR, there's a bit of data. Broadly speaking, it's a power law decay. Its slope is fairly consistent with the X-ray. There's not much more that can be said about that. Yeah. The other IR thing is, of course, the spectrum. So ground-based spectrum, better spectra were basically impossible due to all that dust. So the only thing that could really do it is Webb. So this is Ben Gompert's program. And you can see, so the blue is 250702b's host. And this put the redshift at much higher than we'd originally assumed. So Angela Van led a paper fairly early on, and we'd assumed the redshift was about 0.3, 0.2 to 0.3, depending on which model we used. And obviously this is now at 1. So that makes it pretty energetic, 2 times 10 to the 54 ergs. So it's energetic. It's not the most necessarily energetic GRB we've ever seen, but it's pretty high. And importantly, you can't really see a supernova in this light curve. So this is about 25 days rest frame. So it is post-peak, but you'd still possibly expect some supernova evidence. Certainly if you had AT2023 LCR in there, you'd be able to tell it apart from the host spectrum. But importantly, it doesn't necessarily exclude all supernovae. There is enough wiggle room for a relatively faint supernova to fit under that spectrum. In terms of radio, obviously there's been radio follow-up. I can't really talk much about it, unfortunately, but it's kind of consistent with broadband afterglow. But yeah, I think this is the only paper that really looks, to my knowledge, that really looks at the radio with the correct redshift. But more are coming. Okay, so now I've talked about what GRB 250702b is. I guess I'll talk about what it is more. Okay, so basically it's inconsistent with typical GRB progenitors. It's not a collapsar. It's not a binary neutron star merger or neutron star black hole merger. So we need to find some other kind of progenitor. So there's been quite a few suggestions, possibly some kind of atypical collapsar or a black hole helium star merger. And then the other options are basically some kind of TDE. So I'm just going to briefly talk about all those models. So an atypical collapsi, if you basically have a much bigger, wider star than usual, then it's going to take much longer to collapse. So you can increase the engine duration that way. And then you've got fallback accretion as well, because the material takes a much longer time to fall back. And then you get a much longer GRB-like signal. The assumption is also that you get quasi-periodicity because material falls inwards, gets blasted outwards, and there's a kind of delicate balance between the two. So the so the jet briefly turns off and then turns back on, etc. And you get the repeated GRBs themselves. Okay. So the helium star black hole merger is basically driven by modeling of the high energy emission, which implies a very narrow jet. So if you see in this very narrow jet, a very high Lorentz factor with a minimum variability timescale that's related to the black hole mass, then you require both a stellar mass black hole and a very narrow, and a very high spin. So you need to also insert that spin basically at the time that the black hole is created. So the easiest way to do that is to have a black hole and helium star merge, basically. So then you can produce the GRBs. I think precession accounts for the variability. So this model kind of works as well. The other thing it does predict is a supernova, of course, because you've got a star. But importantly, it's going to be much fainter than a typical collapsar supernova. So there's a couple of reasons for this. First of all, you've got much less nickel available to use. So you basically got the nickel in the accretion disk itself. And the abundance is much lower. But you've also got weaker disk outflows. So you're not projecting the material out further to decay. Okay, so that kind of supernova would fit into the limits that Ben got. Okay, so the other options are some kind of tidal disruption event. So very briefly, they're powered by the disruption and accretion of a star by a black hole. And importantly, they can repeat. We've seen a few repeating ones, 2020 dBl. Things like QPEs, quasi-periodic eruptions, might be repeated disruptions of a white dwarf. Swift JO230, but then there's debate as to whether QPEs are interactions between extreme mass ratio in spirals and accretion disks. And as I said earlier, they classically decay as T to the minus 5/3 or T to the minus 9/4, but that is dependent on assumptions. And importantly, a minority of them do have jets. So in fact, Swift J1644 back in 2011 did trigger the bat multiple times. So we do have a repeating gamma ray / hard X-ray trigger from a TDE. But the difference is that instead of having this 10 to the 5 second duration and then fading, J1644 lasted 10 to the 6 seconds, much longer. And much slower than a typical GRB or even this kind of GRB or an ultra long. But you can accelerate all these timescales a couple of different ways. The easiest way is through using a smaller black hole mass. So this is a super. So here's 1644 in red, and you can see it just lasts. Okay, so like I said, the easiest way to speed up the engine duration in a relativistic TDE is to shrink the black hole. So at 10 to the 4 seconds, at 10 to the 4 solar masses or so with an IMBH, you get this much faster evolution, and the plateau timescale gets you to about a day. So that works in terms of the timescale. The slight difficulty in this model is then achieving the very high energy photons. So Grano et al. Assumed that basically as the accretion disk built up over those 10 to the 5 seconds or so, the accretion rate rose, and this helped collimate the jets, and it essentially boosted the Lorentz factor. So possibly due to reduced baryon loading as well, and that gives you the gamma ray emission. So this assumes a Lorentz factor about 100, I think, based on the fits to the previous data. Yeah, so the X-ray emission, they assume is dominated by the afterglow, which seems broadly reasonable. And then to produce the periodicity, you can have both precession and also if you have instabilities in the disk itself. So you get short boosts of accretion as these instabilities reach the black hole. Okay, the other option, or another option, is a micro TDE. So instead of an intermediate mass black hole or a supermassive black hole, this is a star basically coming in and encountering a stellar mass black hole. So in this case, we've got a slightly different problem to going from a supermassive black hole to an intermediate mass black hole, in that the engine duration is too short. You basically get a very short flare. So instead, you need to, you can extend it a couple of different ways, basically relying on material falling back over the day time scale to the black hole. So the first way you can do this is basically a star comes in, has a grazing encounter, but becomes bound to the stellar mass black hole, and then returns on that day time scale. So you get a bit of accretion at the start from the bit of material that's pulled off, and then you get a proper disruption later on as the star returns. Another option is basically we have a system where it's a binary system and one star explodes, collapsing to the black hole. The other one is fired out and then returns on the daytime scale as well. So you get a bit of accretion early on when that natal kick is introduced, but then you get the full disruption again later on to produce the gamma rays. Or you get some kind of hybrid where the natal kick produces that grazing encounter and then it still returns. So again, like the black hole helium star merger model, the small stellar mass, the stellar mass black hole is consistent with what was observed in terms of the narrow jet, high Lorentz factor, minimum variability timescale. But then you get a predicted slope that is shallower than you observe in the X-rays. Okay, so the final model I'm going to be looking at, and you might be able to guess that this is the one I favor, is a white dwarf intermediate mass black hole tidal disruption event. So because white dwarfs are so compact, they both require an intermediate mass black hole to be disrupted. If not, they'll just basically fall straight into the black hole before the disruption occurs. And that also means that they're very quick events, but even quicker than a normal stellar mass black hole. Sorry, a normal main sequence star. Which means that they are much too quick for the observed timescale. So you've got this single accretion event. This is from Dongyue's paper, or the Einstein Probe team. So you've got this single disruption. You can see it's much too slow. You can slow the accretion down by assuming some kind of viscous timescale. But again, you don't get this rise to the peak. So another option is repeated partial disruptions. So this works out for a couple of reasons, because we've got that periodicity. So that kind of sets a rough timescale that we could see repeating orbits, and white dwarfs are degenerate. So we got another effect there. So if we have the white dwarf being bound to the intermediate mass black hole, then we get these repeated tidal disruptions, repeated flares. So each of these is essentially an individual tidal disruption, fading as t to the -9/4, because it's a partial disruption. And then as the white dwarf expands, you gradually lose more mass over time, depending on exactly how the orbit is balanced, which means they become less bound and easier to disrupt because they're bigger. And eventually you get to a point where the full disruption occurs. And you get this full runaway effect, probably over a very short time scale. The other nice thing about having a bound black hole is instead of a parabolic encounter, the white dwarf bound to the black hole, sorry, instead of the parabolic encounter, you have an eccentricity that is less than 1, which means that the slope naturally steepens. So this is a full disruption, so the slope should be t to the minus 9 5/3, but it nicely follows the t to the minus 1.9, t to the minus 1.8 that we see. And importantly, the accretion rate stays on, stays super Eddington this entire time, so the jet stays on. So the assumption in our paper is basically all of the X-ray emission is from the jet. It's internal processes, there isn't afterglow, which makes things a bit different. Yeah, so this is our fit. We get an eccentricity of 0.92, which very nicely falls into this 0.97 requirement for repeated disruptions of a white dwarf. But also we can estimate the opening angle and assuming some kind of radiative efficiency. And what we find is a much, much lower Lorentz factor than any other model. So we've got something like 2.5 to 13 as opposed to the hundreds or so. The difficulty with having such a low Lorentz factor is then producing the MEV photons. So I have a slightly contrived workaround where basically you have a load of debris streams that crash into each other, and the thermal shock photons that are produced are nicely at about the right energies to be upscattered by the jet to produce MEV photons. So basically, the next part of GRB 250702b story is radio. It can't be seen any other way. It's being observed still, I believe. And the important thing is that radio can, because it's going to be dominated by the external shock most likely, should be able to differentiate between these models. Specifically, it should be able to figure out, constrain the Lorentz factor of the initial jets quite nicely. So because the white dwarf IMBH implies a low gamma ray, a low Lorentz factor, the white dwarf IMBH implies a low Lorentz factor, but also because you've got these repeated disruptions, according to some models, there are repeated jets, so you get a much higher luminosity in the radio. Sato et al. Predict 40 jets, and therefore the luminosity is boosted by something like 40 times. Whereas all the other models basically assume a very narrow jet, so you get a much different radio counterpart. Okay, so there's a few wider implications of 250702b, and the first of which is it's not actually that unique, as it turns out. So this is XRT 00519. This was identified back in 2013 in archival Chandra data. And you can see it's got these two precursor peaks rising to this much more significant peak, and then a relatively flat, slightly decaying quasi-plateau. This bottom plot zooms in basically here. So you've got another peak there and then the main peak. Unfortunately, we don't have a redshift for this. Our web proposal got rejected, so maybe next cycle. So we can't tell if this is a direct counterpart, what's it called, companion to 250702b, but possibly. And the other interesting thing is, going back to QPEs, if they are a white dwarf repeated partial disruption, then GRB 250702b could represent how they die. So basically, as the white dwarf inspirals, you will get this runaway effect, assuming a point it reaches that eccentricity threshold. If not, it will bounce out because angular momentum gets transferred back to the white dwarf. Okay, so to conclude, 250702b is pretty much unique. It's the only repeating gamma ray burst in 50 plus years of gamma ray burst astronomy. It's not consistent with typical models, but there are a few options. I think I favor the white dwarf IMBH, but who really knows? So thank you for listening.
Thanks, Rob, for these very enlightening and very different objects. And I see there are quite a few questions. I think over there was one of the first ones.
Yeah, does anybody analyze the minimal variable timescale for the prompt gamma rays and the X-rays?
Yeah, so the gamma rays have been done. I don't know about the X-rays. The prompt, the gamma ray is, where is it? Here we go. It's about a second.
Oh, yeah.
Where are we?
So it's larger than typical GRBs.
It's kind of in the middle.
Oh, you
Yeah.
okay, I see. Okay.
Yeah,
I see.
it's assuming it's related to the size of the black hole, then it's perfectly sized for a stellar mass.
Yeah. How about the long-term X-rays? Are they afterglows or just like TDs? They have some small variabilities.
So the X-ray is broadly okay, I'll just do this one. So it's broadly flat, or not much evidence of variability. There does seem to be a little bit of an offset between Swift and EP. I don't know if that's a calibration thing or whether it just happens that there was variability, but it's difficult to tell because it's two different instruments.
Thank you.
Okay, next question, maybe Susanna, behind you.
I was wondering if if all these assumptions are fine with the rates. I mean,
yeah,
if they're
okay.
consistent or not.
So Ben and I both had bits on rates in our papers. I think broadly speaking that it's consistent. I'm trying to remember. So mine, we assumed that the rate of a white dwarf IMB-HTD was about a couple of orders of magnitude plus lower than what you typically assume for a supermassive black hole main sequence. And that works out with, we've seen one in Fermi's lifetime. I can't remember exactly what Ben said, but yeah, that the volumetric rate was consistent with what we've seen, I think.
Yeah, so your model inverse accelerates a white dwarf and intermediate black hole model, and you say main mission is inverse Compton. And that case, see the photons around the KB, soft X-ray, and any constraint there, or you need to assume really high Y parameter, or?
So they're kind of just assumed to be there, but we've missed them because the thermal shock basically lasts the light crossing time. So it's going to be smoothed out over a long observation, and it's peaking at like 50 keV, I think. So with FXT or Swift, you're just seeing the tail end of it anyway.
Particular storm.
No, I think you basically, in theory, they'd occur roughly the same time as the gamma ray bursts, and we don't necessarily have strong evidence for them, but there's not necessarily strong evidence against them. I will admit that that bit is slightly contrived. It was a way to get MEV photons with this model. But, yeah.
Okay, we have time for one final question.
Still,
People over there didn't have any chance. No, please not. We don't want injuries.
Sorry for the stupid question. What is a repeating disrupted event? It means that it's repeated, but how? Does it's about the white dwarf.
Yeah.
So does it mean that it breaks the white dwarf?
Yeah, so
because the reason why I'm asking, because that made me think about the Schumacher-Levy comet on Jupiter some decades ago. There was a comet, maybe an asteroid, and it broke.
Yeah,
and there were multiple events on the surface of Jupiter that left a lot of marks on the surface, much stronger than what was predicted. So I was wondering if something similar happened.
Yeah, so that was a tidal disruption event. There's TDEs across the entire mass scale, like white dwarfs can do it to asteroids and things. Basically, the repeated one, it's more tidal stripping is probably a better term. So the outer layers of the white dwarf the star get torn off and accreted. And then, because the star is still on it's effectively a binary with the black hole, or it's orbiting the black hole. it comes back around and gets more torn off and so on. No, it doesn't break. Oh, okay, slightly complicated. Sometimes yes. If it's a very deep encounter where this star can pass, where the star passes very close to the black hole, then some of it can get torn off, but then the star goes past the black hole and reforms over time, and then can return and be disrupted again. Yeah. No. You need to. It needs to be orbiting and then either fall in gradually over time, or you can bind with, say, the Hills mechanism, where you have a binary coming in, and that the binary gets disrupted, and one of the stars stays bound to the black hole.
Okay, we have to stop here. There's still a lot of questions, but you please approach Rob in the coffee break. And thanks, Rob, again. And we go to the next speaker.
Oh, okay. Thank you. This one works too?
Should work, yes.
Okay.
I'd better use that.
Yeah,
Yeah.
I'll just also.
So while we're setting up, our next speaker is, okay, I'll try. Gokul Srinivasaragavan, I hope that's more or less correct, on an EP event / Supernova 250827b.
Okay, sounds good. Hi, everyone. My name is Gokul Srinivasaragavan, and I'm very excited to be here and have the opportunity to talk about some of the work I did at the tail end of my PhD, particularly on an Einstein Probe transient, EP 250827b, and its associated supernova. And I also wanted to use this as an opportunity to give a broad overview of the field of X-ray flash supernovae as well, because this field is being revitalized by the EP and SVOM missions, from which we heard some really great talks about yesterday about. So to start off with, I wanted to ground everyone with some definitions about sort of everything that's in the literature in this field. So I've heard some comments from people that all the definitions that we use are pretty confusing. So I wanted to use this as a moment to kind of just talk about everything, try to get everyone on the same page, and hopefully work towards building a common understanding of how we can actually define all of these terms. So we have FXTs, EFXTs, XRFs, and then these dash supernovae. So to start off with, FXTs, which are the most historically used term, are fast X-ray transients, and they're short flashes of X-ray emission, which last from seconds to a couple hours, discovered in the soft X-ray regime from 0.3 to 10 keV or so. So it's important to note that these are defined by their discovered energy range from 0.3 to 10 keV. It's purely an observational definition. But recently, AP's follow-up X-ray telescope is also abbreviated as FXT. And in papers, oftentimes we actually use the same abbreviation for both. And I've gotten referee reports saying, okay, this is very confusing. We should probably do something about this. So now we have EFXTs, which are extragalactic fast X-ray transients. So these are the same definition as FXTs, but just the extragalactic ones. And for the most part, these are the ones that we as a community are most interested in. These are ones that are associated with core collapse supernovae, with long gamma ray burst-like emission, sometimes TDEs, or maybe neutron-star mergers. But it's important to note that EFXTs, again, are defined by their by how they were found, the 0.3 to 10 keV range, and that they may have accompanying gamma ray emission. There are numerous EFXTs in the literature that do have confirmed gamma ray burst counterparts, even though they might have been found in the soft X-rays. And then we have XRFs, or X-ray flashes. So this is a slightly distinct class of events that is still related to the other two, but they are X-ray and soft gamma ray transients that are defined by their possessing an intrinsic peak energy with respect to their energy spectrum of less than around 30 keV or so. So it's important to note this distinction because this is a physically defined class, not an observationally defined class. Now, this cutoff of 30 keV or so is a bit of an observational cutoff, not really grounded in too much physics, and it's because of the fact that historically, satellites like Beppo-SAX and HEDI were the first ones that started to study these before EP and SVOM. And when XRFs were first found, it was defined by bursts that would trigger Beppo-SAX's 2 to 25 keV detector, but not the higher energy gamma ray detector. But from a physical perspective, there is some credence in using this 30 keV cutoff because less than 30 keV or so, it's hard to have a successful relativistic jet with an energy spectrum that peaks at such a low energy. So now any event that has an optical counterpart that is a confirmed supernova is just a dash SNE. So we can have an FXT SNE, an EFXT SNE, an XRF SNE. That's just referring to the optical counterpart, which is a confirmed supernova. So I wanted to propose that maybe we should stop using the term FXT altogether for these sorts of transients. I understand this is the historical definition, but now that Einstein Probe's follow-up X-ray telescope is also called FXT, it makes things a little bit confusing. So why don't we stick to EFXTs, and then if we're interested in galactic fast X-ray transients, which many of which are interesting, we could have stellar flares, magnetary outbursts, bursts from X-ray binaries. Maybe we can start calling them GFXTs. I don't know, just throwing stuff out there, but I think something needs to be done because things are pretty confusing at this point. And I've gotten a lot of comments from referee reports and other people also agreeing with this. But happy to have more discussion on this later on. So finally, I just wanted to confirm EFXT is an observational definition, while XRF is defined based on a physical feature. So some EFXTs will be XRFs and some won't be. So now getting into more of a physical picture, what actually causes an XRF? So we all know for the most part that for a successful long gamma ray burst, we need to have a core collapse supernova resulting in the formation of a compact object, launching a successful relativistic jet, and we need to be in the line of sight of the jet. So from a purely geometric perspective, if we're not in the line of sight of the jet, we might not catch the gamma ray emission, and these are what are known as possible orphan afterglows, where we only catch the afterglow emission from these systems. But from a physical perspective, what happens if there are no gamma rays produced at all, or if gamma rays are produced and they are reabsorbed and emitted, or they're absorbed and re-emitted as softer wavelengths? For example, what if we have sort of a jet that gets choked by a stellar envelope? What if we have a jet that does escape its stellar envelope but interacts with a dense CSM? What if we have a very baryon-loaded jet that has a lower Lorentz factor and doesn't produce gamma rays altogether? So all these situations are projected to produce possible X-ray prompt emission rather than gamma ray emission. And now that we have EP and SVOM operating, we're detecting more of these as X-ray flash events. So again, if any of these events have an associated supernovae, they're known as X-ray flash supernovae. So now I'll get into the particular event that I studied, EP250827b. And this was an interesting event from a variety of different perspectives, but one of the biggest was that it actually wasn't a bona fide detection by the Einstein probe that was sent in a GCN, and we didn't do the follow-up the usual way we do. So this was discovered through a joint experiment by EP and ZTF, where ZTF actually shadows the public field pointings of EP every single night, searching for optical counterparts. EP sends its sub-threshold X-ray stream to ZTF. ZTF shares the optical counterparts they find, and they try to cross-correlate and find coincident detections. And that was the way that we actually backed out this source. So here's the X-ray light curve. It has a T90 of around 1200 seconds. And at the redshift that we have for the optical counterpart, this is a luminosity of around 10 to the 45 ergs per second. We see a really nice X-ray light curve here with the rise, decline, and kind of teeters off. And here we see the spectrum, and it's best fit by a broken power law, which is in contrast to the event that we talked a lot about yesterday, EP260321A, which is clearly best fit by a blackbody spectrum. But we were able to see that there's a peak energy cutoff of less than around 1.5 keV or so, which lets us know that we can classify this source as an X-ray flash. So I'm not going to have time to get into all of the detailed modeling that we did, but I want to just paint a brief picture of what we think the progenitor system for this source is. And it's important to note that the progenitor systems for all of these X-ray flash supernovae are pretty diverse in the literature. So there's 3 distinct emission episodes here. We have the prompt X-ray emission. Then we have the supernova emission, where the supernova is a type 1c broadline supernova. The supernova usually found in association with long gamma ray bursts. And the type 1c broadline supernova actually has 2 peaks, one at around 2 days or so, and another at around 20 days or so, or 15 or something like that. So in order to explain all these components, we believe this system started from a Wolf-Rayet star that lost significant mass loss. It had significant mass loss at the end of its life, which resulted in an extended CSM environment that is rather dense, forming around the progenitor star at around 10 to 13 centimeters, which is more inflated than what we'd expect for a simple Wolf-Rayet progenitor. And we think that as the star collapsed, it led to a long-lived magnetar, as well as the formation of an accretion disk. So there are 3 distinct ejecta that we think are occurring in the system. We have outflows powered by the accretion disk, we have winds powered by the magnetar that are magnetically driven, and we have the normal supernova neutrino-driven shock. So originally, we have these disk outflows in the magnetically driven wind that sort of mix together, and then they travel at a speed of around 0.3 c or so, which is not exactly relativistic, but it's much more than what we'd expect for a normal supernova shock. And the interaction of this mixed ejecta with the extended CSM environment produces free emission, and we see this as the X-ray luminosity, as the prompt X-ray emission. Then, as this mixed ejecta begins to cool down, it cools adiabatically, and it produces thermal emission, and this produces the first optical peak in the supernova light curve. Then, at later times, we see the supernova neutrino-driven shock, then go through radioactive decay processes, in addition to energy inputs from the spin down of a magnetar, which powers the second supernova peak. So that's the overall progenitor picture that we paint for the system, and I will put a QR code at the end of this talk if you want to look at more of the details. So finally, I want to end off by giving a little bit more of a context for the overall X-ray flash supernova landscape and where things sort of stand at the moment. So here is some spectra of a sample of X-ray flash supernovae, and all spectroscopically confirmed X-ray flash supernovae are type 1c broadline supernovae, which means that they have these characteristic broad absorption features of iron-2 and silicon-2, and no hydrogen or helium, and large absorption velocities. But there's one event that in particular that is interesting, and I talked about this briefly yesterday, supernova 2008d, which is actually a type 1b supernova, and it shows clear helium features in the spectra. Here we see some of the X-ray flash supernovae detected by EP, their light curves in comparison with GRB supernovae, 1C broadline supernovae, and type 1b supernovae. What we find is that their luminosities are pretty similar to the GRB supernova population, and they are a little bit higher than the normal type 1c broadline supernova population that are optically discovered, and much higher than the 1bc population. So finally, I just want to briefly go through this slide and give a little bit of numbers for how things are looking right now. These are all of the X-ray flash supernova that was discovered pre-EP SVOM, and then we have the ones that are discovered during EP and SVOM. Big takeaway here, there's already more events that we discovered in the past 2 years than we have all throughout history because of EP and SVOM. So, TLDR, we're in the golden era for X-ray flash supernova science, thanks to EP and SVOM, so let's capitalize. Thank you.
Thanks to Gokul for keeping very well in time. We have time for 1 or 2 questions. No questions?
Hi, nice talk. Can you give some comments about prompt X-ray emission? I think the spectrum is very soft, and can it be fitted with a just a black body model, or we can't distinguish that?
Yeah, so we can fit it with a black body model, but statistically it's not as good as a broken parallel model. But with X-ray spectra, especially because we don't have a lot of counts, it's hard to make a distinguishing kind of thing unless it's like clearly a black body spectrum, which was the case for the other EP260321A event we talked about yesterday. So that was probably a bona fide sort of shock breakout. Again, it kind of begs the question of what exactly is a shock breakout, which Wynn brought up a good point about that yesterday. But yeah, that's sort of the story with the X-ray spectra.
Thank you.
Do you have another? Oh, there's another question.
Thank you very much for the nice talk. This comment about them all the supernovae being broadline 1C supernovae, is this expected, or do you think that if you get enough of these objects, you will start to find a larger diversity in the supernova counterparts?
Yeah, that's a good question. I think I would expect that we do have one type 1b supernova, supernova 2008d. There hasn't been one since then. I think with EP, we're expected to discover more of these shock breakout events, like the ones like EP260321A, than we have discovered so far. I think the more bona fide sort of prompt X-ray spectra that can be fit with a black body, more of a normal supernova shock breakout, I think those are the events that might have more of a chance of us detecting not being type 1c broadline. I think the ones that are type 1c broadline, they probably have some sort of either a jetted component or at least something that's depositing a little bit more energy than what we'd expect for just a normal supernova shock breakout. So I think with time, we'll kind of see whether that comes to fruition or not. I think that there probably is going to be another type 1b supernova shock breakout associated with one of these events, but we'll see.
Okay, thank the speaker again, and we move on to the next. So our next speaker is Benjamin Schneider from here. He's very local, from Marseille. And he has another interesting object, XRF 241001A, which was in this case detected by SVOM.
Right. Okay. Hi everyone. So I am Ben Schneider. I'm a postdoc at LAM in Marseille, and I'm going to talk about the X-ray flash 241001A, which is a work that has been made as part of the SVOM collaboration, and include a lot of people from SVOM and broader than that, with many expertise. So I'm going to be quick on the context. Gokul already introduced a bit of that. Basically, X-ray flash is similar to a GRB, but is dominated by X-ray photons. Typically, we are using this threshold, which is not usually, sometimes difficult to classify. We have discovered this event about 20 to 13 years ago, but up to now, we only have a small sample. This is mainly due to the fact that Swift and Fermi are not designed to detect this population. You can see here an histogram that show a bit the population with typical GRB, another type of population that I won't describe, but you can see here the typical statistic that we have so far that is very limited. So here I listed a couple of possible origins, but we are not sure what is the fraction and if there is more diversity or no. But as it was mentioned, SVOM and EP are now here, and we are able to detect more and more and characterize this event. Okay, so here you can see an animation of what happened for this event on board SVOM. So at the top here, this is the count rate as a function of time. So you can see here a little bump, which is this event. And at the bottom, you can see here, this is 2D images. You can see here, this is typically what the detector is seeing. So it's pretty hard to see anything here. But here, it's when you have a deconvolve from the coded mask, and you should be able to see a point-like source. It's, I would say, pretty tough, but if we stop at the right moment, you can see the source was at the left edge here, and this burst was detected during the commissioning phase of SVOM, so it's important to keep this in mind. This means that we're in the discovering phase of the mission, and all the feature was not enabled for SVOM. So it was a very faint and soft event. I think it's still among the faintest event that has been detecting during the 2 years of the mission. I trigger on the lowest energy band possible of SVOM, so between 5 to 8 keV, and here you can see the duration that was pretty short. Okay, so here you can see the signal in different band from the prompt emission. You can see that main, to not say all, the signal is detected in the 4 to 20 keV. So depending on how you've been, you can see a little bump above, but it's not very statistical robust. On the right, you can see here, this is a spectrum of this emission. We tried to fit both a thermal, non-thermal model, and you can see that it's very difficult to distinguish between the two. It's due to the fact it's very soft and also really faint. But as you can see, the E peak is very low, between 6 to 7 keV, and it's clearly classified like an X-ray flash. So there is some way to, there is a way to classify events, but it's so faint that we cannot really apply in that case. So there is some ongoing work with the first SVOM GRB catalog to try to adapt this classification method for the burst detected by SVOM, and it's led by Olivier Godet. So we managed to detect the optical counterpart about 1.5 hours, so which is not too fast. Usually we can do much better than that. And then we managed to secure an X-shooter spectrum of this source as part of the Stargate collaboration. You can see it on the right. So there is 3 arms in the UVB, VIS, and near infrared. So in this spectrum, we observed absorption line and also emission line from the host galaxy. So we have a pretty secure redshift using this information that is about 0.6. And something I would like to raise is that you can see here there is a very blue emission that is not typically observed for a GRB event. Okay, so if you use this information, we can derive the isotropic energy and also the E peak. Here you can see the isotropic energy as a function of redshift, the position of this burst that is clearly below if you compare to X-ray flash detected at similar redshift of long GRB, it's clearly below. And at the right, it's something we have seen already yesterday. It's the amateur relation. You can see the E peak as a function of the isotropic energy. And again, the position of this burst. So as you can see, we start to populate this region of the amateur relation, but it's still for now poorly populated. Okay, so something we investigate is if Swift would have been able to detect this event, as Swift is currently as a baseline. So we use the Swift BAT GRB catalog, and here you can see the 1 second peak flux as a function of the fluence. You can see here all the bursts that has been detected for Swift, and you can see here if you derive this measurements for the SVOM burst, you can see the position that's clearly an outlier in this diagram. So very likely, SVOM will not have been able to detect this event. So we're clearly able to probe something different with SVOM here. Here you can see this is the afterglow emission. On the left, this is the X-ray afterglow. You can see here the position of this event compared to what has been detected by Swift in gray. And in blue is if you limit to the GRB supernova event at a similar redshift. Here also you can see if you just take one given time, the distribution of the luminosity and the position of this X-ray flash. So on the right, this is similar plot, but for the airband magnitude, so the CAN plot, if you know it. So you can see again in background in gray, this is a GRB that has been detected by Swift, and you can see the position of this X-ray flash. So in both X-ray and optical, it was at the very faint end to what we have detected so far. So as I mentioned previously, we have observed this very blue emission in the X-shooter spectrum. You can see here again this emission that we tried to fit using a combination of the thermal model, like a black body, with a power law. And you can see the fit that you can get. And something that is interesting is that this kind of emission that was also observed in some EP events. Here you can see one of them, a spectrum from GTC that was obtained at a similar time that also showed this blue emission, and we also compare to the F-boat, the CO, but as you can see, it's a much later time with this blue emission. So the origin is not clear at the moment. We still have not a lot of events like this, but possibly it can came from raised from the shock at Cocoon. And something that also need to investigate is this may be, I mean, something common that is observed, that is produced by all GRB, but may not be detected if the afterglow is too bright. And here we may be in the case of the afterglow is very faint, so we can also see this emission in addition. Okay, so here you can see this is the multi-wavelengths afterglow, I mean the multi-wavelength data. So you can see we don't have a great sampling of the emission, but we still tried to model. We use in particular redback for that. So you can see the typical decay from the afterglow and then the bump that is typically observed when you have an associated supernova. So we modeled that using a Topat jet, an Hornet model for the supernova. We also tried a more complicated a model like a structured, but here I will only discuss this one. And we use two different data sets because, as I mentioned, there is also this thermal emission that will not be a model as an afterglow. So we tried to remove it. So we have not many points, but we had also to remove some. So then it was pretty challenging. But you can see here the resulting modeling for the both data set. And I think the main result here is that the burst was seen on axis. I mean, the modeling suggests that. And from both modeling, we also derived a very low gamma ray efficiency when you also compare to the prompt emission. Okay, so coming to the James Webb observation, so we obtained at the expected supernova peak near spec observation. This was part of the Ben Gonper's program. There is a talk on Thursday about this. And here in red, you can see this observation from Webb, and we have a clear detection of a supernova. That is an excellent match with 1CBL supernova that is typically associated to supernova. You have other examples here from the archetypal 89 BW, and also another one that was associated to an EP event and observed as part of this program as well. So there is some interesting features in the near infrared that is still, we are not sure what there are. Can be some helium one blended to some other elements, but we need to investigate this on a larger sample that is building as part of this program. But this, the main result is that this firmly established as a collapsal origin. I will go quick on that. It shows a bit the property of the supernova compared to previously detected GRB supernova and for the F2 and Silicon 2 line. So you can see it's pretty typical. Here, this is the energy of the supernova and also the peak absolute magnitude. So it's pretty similar. And I think here the main result is that the prompt was faint, but the supernova associated was pretty typical to what we have seen. So there is, it has been shown in the past that there is likely no correlation between the GRB property and the associated supernova. And this, our result is going towards that direction as well. And just to finish, this is for the host galaxy. We have no detection for the host, pretty deep for the redshift, but it's not unusual for GRB or X-ray flash host galaxy. Something quite interesting to show you how the James Webb data can be rich. If you look at a 1D spectrum at far from the supernova emission, we have seen some emission line here that is a bit shifted from the host galaxy, from the redshift of the host galaxy. So we think there is possibly a companion or some outflow. It's difficult to say without a high resolution imaging, but there is probably a complex system here. Okay, I was a bit long, so I will leave you with my conclusion here. So just to say that the paper was accepted yesterday, and you have the first version of the paper on archive if you want to check out. Thank you.
Thanks, Ben, for this nice talk. We have time for one question. Is there one question or online? Everything clear about SVOM X-ray transients? Up there.
Thank you very much. Can you go back to the slide where you showed the James Webb supernova spectrum, please? I only got a quick, no, the one before it.
Sorry.
Yeah, so I only got a quick look at this. This is sort of related to a comment that Gokul made yesterday or whatever. So broadline 1C supernovae can have 1 and 2 and 4 micron helium lines. It's more, so do you interpret this as helium absorption at 1 micron? Or do you think it's something else?
So it can be a blending of a C1, carbon 1, and also helium 1. But there is probably, blended line here. But
do you think the 2 micron absorption is helium?
No, that was suggested in the EP paper of Jianhe. But as you can see in that event, it looks not really here, I would say, at 2 micron. For sure, the 1 micron is seen in both. So they try to do some modeling of this to see if there is possibly some helium, but I think it's still, we need more data to investigate this deeper.
So sort of just something to be aware of. So we looked at this for Gillian's paper for 25 kg. The classification of supernovae historically and probably incorrectly is based on the presence or absence of helium lines in the optical. So you can have strong absorption for helium at 1 and 2 micron, and that does not mean that it's not a broadline 1C supernova. So this could very well be helium in a broadline 1C supernova. It's just something to bear in mind for these objects, because this has come up now a few times. So
yeah,
it's probably okay. You need very, very little mass of helium to actually do this. So it doesn't mean it's a 1B broadline or something. So.
Okay, so thanks again to Ben, and we move on to the next speaker. Our next speaker is Jennifer Chacon on another Einstein probe, FXT, EP 240806A.
Hello, everyone. My name is Jennifer Chacon. I'm a PhD student at Pontificia Universidad Católica de Chile. So I come from a very distant place. And I need to say this because the Chilean Astronomical Society supports my trip. So yeah, that's why I'm here. And today I'm going to talk about this interesting source, which is EP 240806A. And thanks to Benjamin and Gokul, I think I might need to skip a bit this because we know that the possible progenitors of fast X-ray transient or extragalactic fast X-ray transient, as Gokul suggested, if we increase the peak X-ray luminosity, we can have supernova shock breakouts, then binary neutron star mergers, tidal disruption events, and gamma ray burst. These statistics are not as well updated as the ones that Wenxian showed yesterday, but only to remind that thanks to Einstein Probe, we have detected more of these events, and some of them are very related to gamma ray burst afterglows. And it's very interesting because we have from the 300 and so events that Einstein Probe has detected, 223 or more are these extragalactic fast X-ray transients. We have optical counterparts for more or less 90 of them, and we have confirmed redshifts for more or less 53. As well as I mentioned, these statistics are better explained in the talk yesterday. And the common suspect for explaining the relation between those two phenomena can be the collapsar scenario, as also Gokul explained. And whether we have a gamma ray burst or a FXT. It depends on, for instance, the jet outcome. For if it's a shock jet, we can expect a soft X-ray dominated emission, that's an FXT, or maybe if the orientation is off axis, we can expect as well an FXT. So that leads us to this event that I had this approach when I went to New York in December, and I started to analyze the X-ray data. So we have here the, oops, sorry, the light curve. It was detected, well, when we analyzed again the data, we saw that it is 40 seconds later than the JCN value reported. And the follow-up X-ray telescope did the detection in 1 hour later than the WXT. So what we did here is to feed a absorbed power law model, and we get a, I don't know if I can point, yes, a soft photon index, which is interesting for this event and kind of start to give us some details. And next, what we try to find out is if there was a gamma ray signal, and we did it with this tool, Rapid GVM, that make us, clearly we see that Fermi was covering this part of the sky, but there was no gamma detection. Also, we looked into sweep by Guano, and there was also no gamma detection. Here we can see what we try to look in the, thanks to the Rapid GVM tool. But if we adjust as in a bank function, we can derive some upper limits for the gamma rays. Taking into account that the epoch will be 70 keV and the indexes had that values, we can end up with a flux limit of 8 times 10 to the minus 9 ergs per centimeter per second. So this leads us to think about these possible scenarios of X-ray reach or an X-ray flash. And when we try to find out what happens with a light curve, with the X-ray light curve, we see that it rises, it has a steep decay, and then a more shallow decay. And there's a source that is indeed related with a gamma ray burst that has like a similar behavior, more or less. But the fact that we need to stand out here is that the energy band, because we have here a gamma ray detection, if we compare these two, we find that our source is a bit weaker in the energy band for this source. So this can imply that we are dealing with a softer prompt emission component. And then we move to the optical detections. So we have different telescopes that observe the field: LCOGT, Kate, Gemini Nord, Liverpool, NOT, GTC, and BLT Hawkeye. So these images show what we had in catalog image from Legacy, what we detect in Gemini, and some of the Hypercam and Hawkeye bands. So clearly, these are taking at almost 4 days, and we are starting to see that the source is fading away. So not longer than 4 days, the source was not detected anymore, because at this time it was about 25 magnitude in AV. So we also obtained the spectra with Gemini Nord, and we can find two basically intervening absorption systems. What we think is the host, because of the iron 2 and silicon 2 fine structure lines, and another intervening source, 2.818, which was the value that we were previously announcing in GCN as like the value of the redshift of this transient. And then we move to a extended light curve combining both X-rays and the optical. We have, in some cases, some upper limits. We have some detections. For sure, R-band is where we have more of the data. And this is interesting because we try to fit this with a Gaussian jet afterglow model we use in Redback. And this leads us to think that in this follows a typical afterglow decay. This angle, for instance, from the jet is very well constrained, as well as the jet core angle, I guess, and also the photon index. But some of the parameters can be twiggled more. And another interesting thing that we try to do is to look at the SCD, taking the first epoch of FXT and trying to extrapolate it like this and see where it lies with the optical emission, taking with the epoch of Gemini. This is this extrapolation is made in a time window where the values lay at the same time, right? And this is interesting because we put this value in R band with corrected with extinction as well here. So we try to figure out if thus was sufficient to explain this gap. And another thing we try to do is to compute this spectral optical to X-ray index, which is a clear sign of whether we classify a gamma ray burst into this optical dark. This is kind of interesting because, yeah, we say optical dark when we don't have optical emission. In my case, we do have optical emission that fades really fast. And when we compute this value, the criteria is that it's optically dark if it lies here as this source. In my case, it lies very close, which is interesting as well. And as we cannot explain with the extinction how this can be, how this gap can be. I think what our theory lies in that because it's at redshift 2.84, maybe it's the Lyman-Forest absorption what is making this source behave like this. And another thing we try to do is to place the source in the optica, in the peak X-ray luminosity versus redshift. So we have some sources that are indeed GRBs and some that are not GRBs. I'm sorry if you cannot distinguish the colors. I think, yeah, I put them very similar. But our sort like here with a luminosity almost to the 10 to the 50. And yes, with all of these features, we think that is a good way to say that we can consider AP 2408068 as a relatively typical representative gamma ray burst. But we need to take into account that we have a very soft from the emission, right? So it's well modeled by a collapsed afterglow model. We did it using Redback. So this supports the growing sentiment that a significant fraction of the FXTs are related to gamma ray bursts. It was pointed out, I think, in O'Connor's paper, it was last year, I think it was last year. And this moderate optical deficit can be explained not by those, as we try to point out, but this Lyman suppression because of the high redshift of the source. So that will be it. I'm open to questions if you have one.
Thanks for Jennifer for his nice work. We have time for one question. Over there.
Hello, thank you for the talk. Could you define what an XRR is and how that compares to FXTs and XRS,
yes.
etc.?
So XRR as X-ray rich, and I don't remember if Benjamin showed. There are some regions, if you consider the different influences in different energy bands, where you can define whether it's gamma ray burst, against red flash, or an XRR. In my case, because the epoch is not well constrained, it's hard to point where this source lies. But if we assume if we do some assumptions, we can try to feed it there. but it will be very spread in my case. Yeah.
Okay, then we have to move on to the last talk. Thanks, Jennifer, again for the talk. And our next speaker is Jianhe Zheng on XRTs produced by off-axis Jet-Cocoons from GRBs.
Yes. Hello, everyone. Good morning. My name is Jianhe from Nanjing University. Today, I will give a talk on my recent work on the fast X-ray transients. This talk is based on our recent two papers. We are trying to answer a simple science question: how can off-axis gamma ray bursts produce fast X-ray transients? First, let me introduce those fast X-ray transients. They are rapid X-ray flashes on the sky, and before Einstein Probe, they were mainly discovered in the archival data in the X-ray satellite. For example, this figure shows the FXT candidates in the Chandra archival data. Before Einstein Probe, they are rare, short-lived, and usually have poor multi-wavelength information. So we don't know what they are. They could be related to any stellar explosions, relativistic outflows, but without multi-wavelength information, we don't know what it is. However, the situation has dramatically changed after the launch of Einstein Probe. EP is discovering many FXTs. Like in the first year, they discovered more than 63 FXTs. And a very interesting fact is that in this sample, 80% of them have no gamma ray counterparts. This is the answer to Dan Play's yesterday's question. And noting that all of them have gamma ray monitor coverage during the X-ray phase. So we know the majority of FXTs do not have the gamma ray counterpart. They are gamma ray dark. Why they are gamma ray dark? Are they a completely different class? Why we are so interested in these gamma ray dark FXTs? Because for those gamma ray rich FXTs, we know they are GRBs. We have already know that for 20 years, and we know many things of that, and many evidence supports they are connected. The question is, the real puzzle is, how about those 80% gamma ray dark FXTs? Are they totally different, or they are similar but just some other difference? In this talk, I will argue that part of these gamma ray dark FXTs can be explained by the off-axis gamma ray burst. Why? Let's recall the standard picture of gamma ray burst. Okay, this is the picture that Lauren was looking for yesterday. Yeah, the GRB, it comes from the relativistic jet, just like this picture show. You have a central engine and you launch a narrow jet. If the jet is pointing towards us, we see the gamma ray burst, and then the following is the multi-wavelength afterglows. But this picture is incomplete. The system has more or has more. For example, the system has a star. Yeah, for long bursts, you should have the star. So what if we have the star? The system is more complex. This is the realistic picture of the jet within the star. The jet has to penetrate through the star. So when it is propagating within the star, it has this structure, which we call jet-cocoon structure. Because the jet is hitting the star, so you have a forward reverse shock system in the jet head, and the shocked star and the shocked jet will cross the shore and then be heated, and then be pressurized, then float sideways, and then form a cocoon around the jet. The cocoon is the central object in my talk. And if the jet successfully breaks out from the star, the cocoon will also break out. So finally, is the jet with the surrounding cocoon breaks out. This is very important because the cocoon is wider than the jet. That means if we are looking at from large viewing angles where the prompt gamma ray from the jet is missed, so you see no gamma ray burst, but you can see the cocoon. This gives us a natural way to connect gamma ray bursts with the gamma ray dark FXTs. So for on-axis observer, okay, you see the ordinary gamma ray bursts, But for off-axis observer, you see no gamma bursts, and potentially you can see some cooling X-rays if the cocoon is mildly relativistic. And also that explains why GBN and BAT didn't see that, because they're seeing X-ray. And you will see other less beam components like the UV component and maybe the off-axis jet afterglow. And eventually the type 1c supernova is they are less beam. So the key message is, if you miss the jet, you see the cocoon. And I'm introducing the basic physical radiation mechanism for the cocoon emission. Cocoon is different because it's shock heated, it cross shock and be pressurized. So it is thermalized. It's different from the jet emission. When it freshly breaks out from the star, it initially has a very high optical depth, so the photons are trapped within the cocoon. But cocoon can expand, and optical depth will decrease. Finally, when the cocoon reaches the diffusion radius, the photons can escape from the cocoon, and then the emission of the cocoon is therefore released around the diffusion radius. The cocoon emission is very different from the jet emission, the prompt gamma rays. It's more close to the thermal emission we see in the supernovae. How do we obtain the cocoon's light curves? That's what we do. We combine the hydrodynamical simulation and the post-processing method to calculate the cocoon light curve. Here is the video. First, we simulated the hydrodynamical simulation. The central narrow beam is the jet, it's deepest color, and then something surrounding that is the cocoon. And here is the stellar envelope, the star radius is going to penetrate through the star, and then it breaks out, and then you see the cocoon expand sidewaysly, and then move forward to larger and larger radius. We run this hydro simulation to the diffusion radius so that we can capture the emission of the cocoon. Then we do some post-processing method to calculate the radioactive transfer, and then we obtain the spectra in the moving frame of the jet cocoon. Then we do the Lorentz transform, because some of them are relativistic, to obtain the light curves in the observer's frame. So finally, we have our observed light curves. This method allows us to have the cocoon light curves for any arbitrarily viewing angles. And is our result. It's the result of the bolometric luminosity and the color temperature. So on the left panel, different colors are different viewing angles. The cocoon light curve, they are differed by the viewing angles. For the smaller viewing angle, you can see they are very bright. They are as bright to 10 to 48 ergs per second. For those small viewing angles and larger viewing angles, they are fainter, but they are still bright to 10 to 46 ergs per second. And the emission band is changes. You can see the color temperature. They evolve from the X-ray band at early times to the UV optical band at late times. So the cocoon is a natural multi-wavelength transient. And I will talk about the FXT phase, the X-ray phase first. The left panel shows the X-ray light curve for the EPWXT band is from 0.5 keV to 4 keV. You can see that they are bright and they can be detectable by the EPWXT even for the redshift and 0.7. And if you are at large viewing angles, it can only be detected in the nearby universe. And the right panel is the spectra. Just like I said, the cocoon is thermalized, so its spectra is close to thermal. It's quasi-thermal. It just looks like a black body shape. And in the EPWXT band, where is a very important feature is that the spectra is soft in this band. So if you try to feed the spectra by the power law function in the EPWXT band, you'll probably find a soft spectra whose photon index is softer than 2.5 or even 3 or something. It's a very important feature because it helps us to select cocoons from the EP samples just by checking the photon index of them. It's a very easy way. And also this softness tells us that cocoon is very different from the jet because it has a different population on the Amati diagram. Here I plot the Amati diagrams. We know that long GRB follows Amati diagrams in this blue line and blue bands. But he has this long GRB Amati diagram, but our cocoon is different. You don't have to follow the Amati diagrams. So it has a distinct population. You see these points on the Amati diagram, totally different from long GRBs. And yeah, it answers yesterday's question, where are the dirty fireballs? They are in here. They are also in this cocoon-like region. And EP is discovering many FXTs in this region, like Benjamin's source is also in this region. So we have many candidates. And finally, I will compare our model to one of the candidates. But now, let's end with the cocoon emission. And okay, we end with the X-rays. Now we can see the opticals. And it has the optical, they have a blue optical transients at 1 day before the supernova comes. And the temperature is about, is over 10,000 kelvins, and the bolometric luminosity is 10 to 42 ergs per second. Now the viewing angle difference is almost disappeared, so it's a good result. And because it's hot and blue, so optical luminosity is a little bit fainter, but it's still detectable by those wide field optical surveys like WFST, LSST, and Argus array, something like that. It's very important because it can help us to identify the origin of those X-ray transients. And this slide shows I think is the best compelling candidate for the cocoon, which is EP240414. This source let's see what it has. It has a soft prompt X-rays at 100 seconds, consistent with the cocoon, and it has a blue optical UV emission at 1 day. It has an off-axis jet optical afterglow, a bright radio jet light afterglow, and a 1C broadlight supernova that is very close to the 1998 BW spectrum. And finally, there's no gamma ray counterpart. The redshift is 0.4. We should not miss the gamma rays if the redshift is so low. And for this source, it is fully consistent with the off-axis cocoon picture. Of course, in comparison, somebody proposed the on-axis weak jet model. It may explain something of the because the on-axis weak jet also has two cocoons, so you can explain the optical and UV. But it's unclear whether you can provide you can produce the bright afterglows like the off-axis case. And you can see our paper to find some details. We also have other candidates also listed on our papers. And this model difference can be tested in the future. A very important test is in the UV band. So our model predicts there are some UV flashes in a few hundred seconds because this UV emission at the Rayleigh tail, the low energy tail of the prompt X-rays. And you can see that they are very bright, 10 to 43 ergs per second, and they may be detectable by the UltraSat satellite, which will be launched in next year. So it's a good chance to test our model or to distinguish our model with the on-axis weak jet model. And this is the summary of my talk. The off-axis jet cocoon can produce FXTs and other multi-wavelength transients. And EP has discovered many candidates, and a way to test our model is in the UV. The key message is one sentence. If you miss the jet, you should see the cocoon. Yeah, thank you.
Thank you, Jianhe. There's a question over there.
Yeah, so have you estimated the event rate, example, relative to gamma ray burst?
Yeah, event rate, you can imagine the event rate is a gamma ray burst event rate times a factor. The factor is corresponding to the viewing angle, right? So the event rate will be 1 to 10, depends on the viewing angles. Yeah. So I said only part of the FXTs can be explained by because as far as I know, the EP's total FXT rate is higher than this rate.
So you consider only geometrical thing.
Yeah.
And the cocoon emission is dimmer, and maybe
Yeah.
distance, critical distance,
Yeah.
observable distance could be shorter. It's really matter, or you care only?
Yeah, you can only observe like 0.7, redshift 0.7, 0.8. That's the maximum. Yeah.
Okay. Yeah. Thank you.
Okay. Next question.
Thank you for the nice talk. I was wondering if you have an explanation for why your models predict essentially constant temperature for all the variation on the model for this cooling emission, 0.8 keV, and if this may depend also on the progenitor structure, which I guess you did not vary across the simulations.
I don't think we have a constant temperature because you can see it's decreasing.
You mentioned that let's say the peak temperature of this cocoon emission is 0.8 keV independent of EISO, no?
Yeah, because they're averaged by the T90. So you can see this cooling. So it crossed from the 4 keV to 0.5 keV. So the mean of that is about 1 keV. So it's less than in the 1 keV. So because that's the average spectra. Yeah, that's one thing. And another question is about the lines, right? It may have some lines, but because they are for the 1 day optical transients, the chemical composition. I'm not sure the chemical composition, but because they are they are mildly relativistic. I should not say mildly. Okay, their velocity is about 0.2, 0.3 C. So you can see if they have a line, they will be very broad. So maybe the lines will overlap. So you may become something like featureless, but maybe you can identify 1 or 2 lines, but they will be broad line. Yeah. Do I answer your question?
I did not actually ask about the lines, but I asked if you have a feeling of whether the emission that you predict depends on the structure of the progenitor, on the assumed structure, stellar structure.
Yeah. We use the start model of we use one start model, and the start model can affect our results. We didn't investigate it in this work. We may do this in the future. Yeah, it's possible. Yeah.
Thank you.
Okay, one quick last question. I don't want to keep you from coffee.
So thanks for the nice talk. I'm actually a little bit confused about what component so EP2404 14A had sort of 3 phases to the light curve, and the common interpretation in the field at the time was that this is a jet afterglow and cocoon cooling at least, and then the broadline 1C.
Yeah,
where are you saying it's dominated by the cocoon afterglow?
That's the fourth picture of 2414. So the first 100 seconds is dominated by what we call the cocoon. So there's the cooling X-rays, and they have a soft spectra. And here you have X-rays. After X-rays, that's non-thermal X-rays. So maybe cocoon afterglow. And here you have the thermal cocoon component in optical. And here you have the off-X jet afterglow. You see it has a rise in optical band, and then the 1CBL. That's the full picture.
That would get the deceleration peak wrong. Like, that's too steep.
Yeah, you see this 1 day. Yeah, just a few days for it's too long for the deceleration.
I think it's too stark. I'll chat later. That's fine.
Oh well, our cocoon is mildly relativistic, so gamma is like 10. So it should deceleration very quickly, not like supernova. Okay, we can discuss later. Yeah.